some names I don't recognize and some I do. Again, my name is Werner Jud. I'm part of the Great Saltpeter Cave Committee. And Stephanie asked me to talk a little bit about the compass stuff. I'm not going to make this like an in-depth lecture about compasses and uh, the history that goes back. All that's kind of interesting though, but I want this to be more an informal discussion. I just want to share what I have learned about compasses and how to use them and how they uh, are very helpful if you're one of those people that like to hike in the woods. Um, Compasses don't really have a lot of relevancy to most people these days. We are in a high-tech world. Everyone's got GPS in their smartphone, on their cars screens. In fact, somebody knows exactly where you are at every second. And when you're in familiar territories, you just look at landmarks and things that you know to make sure you don't get lost. But if you're a person that likes trees and like to go out in the wilderness, or say out west in the deserts or different parts of the country that are undeveloped, it's very helpful to understand a compass, how to use it with a map and even without it. So I wanted to bring up a few terms about compass reading that I think people have heard about, but they don't always capture or retain it. And reiterate, if you listen to this and you have a question pops up in your mind about it, just shoot it out. This is more of a talk about the whole thing so that everyone feels comfortable. I took some notes in case I fall off my thought train. I can get back on. There are two types of compasses that people use, and I drew or I brought the two that are most common. The one I didn't bring, which a lot of you might recognize from your caving experience, is a Sunto. I used Suntos when I mapped caves. But the basic compasses out there are the base plate compass, which I'm not sure if you can see that one, but it's this. This would be very helpful if we could actually do this in the field someday, and that people can have compasses and we can actually sight with them and look at a map. So you can think of this more as an introduction to a time we can do that, maybe this spring.
Perfect.
So this is the base plate compass, and some of you might be familiar with it or have it. And then the other one that has been around forever is the lensatic compass. So I'm sure you can see that one. And the lensatic compass is the one that is often issued to the military. Hell, I got one when I was a Boy Scout. I didn't know how to use it. The difference between the two, base plate is self-explanatory. It's a compass actually mounted on a piece of plastic with a mirror. That's an important part of it. There is a mirror to sight with it. And the lensatic compass is a compass that you actually look through a lens that magnifies the dial so you can see what your bearing is. Both of them have good uses, and both of them are accurate. I prefer the base plate compass personally because of something called because of the ability to adjust for magnetic declination. So I brought a little show and tell here. This is the Earth. I can hold the Earth in my hands. If you have a globe at home in your desk or study or somewhere, take a look at it. Compasses point to the magnetic north. The original compass was a piece of lodestone that was hung on a string. And it was interesting to notice that no matter how you moved or turned, the stone would always be oriented in the same way. If you want to use a compass with a map and you want to find your path. You have a target. It's maybe a mile away. I'm thinking of how I use it and how most of us would use it as cavers. You're hiking in the woods and you're going through some forest or woodland area, and maybe your cave, is generally in this particular area of the map, but you're not solid, trend that way. Now, if you're in an open field, you can do what most people did for 10,000 years to find their way. They look in the distance and find a target, a piece of landscape, a mountain, a valley, or something, and say, that's where I want to go. And they start heading there. But you can't do that at night. And you can't do it if it's heavily forested. You can't see more than 100 feet. So you have to stick to a trend. And the trend is done by the compass. When you have a map, again, with caving in mind, most of us should be familiar with topographic maps. That's how I started with caving. On the bottom, it says how to orient, or it shows you where true north is. If you look closely on maps, it'll say true north, TN, and MN to the left of it, or to the right of it, which is magnetic north. Let me explain that part, and then maybe a lot of other things will make a little more sense. In this little globe here of Earth, true north is where all the longitude lines converge at a single point. It's an imaginary graph. It's a geograph, a geographic north. That's what true north is. It's just a place mathematically where all these lines converge. And everything on the planet is defined by the geographic coordinates, longitude and latitude. And you all see that on your GPS all the time. You look at a location or you go to Google Earth, somewhere in the margin, it flashes by the degrees, minutes, and seconds of the longitude and latitude. That's at the center, at the top. Magnetic north is not imaginary. Magnetic north is a real thing. It's near the true north, and it moves constantly. About every 3 to 5 years, maps get updated with a new magnetic declination on it. I use a program called CalTopo on the computer that can zoom into any spot on the planet, show you a topographic image of it, and it'll say in the margin what the magnetic declination is for that area. We're in Cincinnati, and the magnetic declination for Cincinnati, which is hard to see on this image, I guess, is -6 degrees. That would be 6 degrees west of true north. So how I try to explain that is that you draw a line from geographic North Pole, that imaginary spot, and you carry it straight down all the way to the South Pole. Then when you know the magnetic deck, which is where the magnetic North Pole actually is, and it moves, I know now, or I know from looking at my CalTopo program the other day, and also you can check it. You can Google magnetic deck and enter your location. It'll instantly tell you what it is. For us, it's about 6 degrees west. So, and it happens to be very far north of Canada right now. It was in the Greenland area about 15 years ago, and other times it's closer to Siberia. But right now it's about 6 degrees west of true north, way far. So that creates a line from magnetic north all the way down to the South Pole. There's an angle there, a parallax. So if you're in Cincinnati and you use a compass, your needle will point to magnetic north, not true north. If you want to get to a specific destination, you have to compensate for the magnetic declination in your compass so that you don't get off course. If you're hiking a half a mile in the woods, you probably won't miss your target anyway. But if you're an airplane or a boat, it gets real important the farther out your target is. If we were to go to Kansas City, for instance, if we went to Kansas City, we could draw a line from the North Pole through the magnetic north, and there would be no deviation. So the north needle would point at true north because we're in the same line as that. But if we were way over here in Asia and the magnetic north is here and you're in, where would you be? Let's say you were in, I can't hardly read that, Japan, let's say Japan or China. And you draw a line to the magnetic north, and then you draw another line to the true north, you'd have a different angle and it'd be, say, 8 degrees east. That's a lot to take in. But the reason I like the base plate compass is if you have one, look behind it, and there will be a little adjustment you can make to your painted north, which is the true north, versus the magnetic needle. And you can adjust the declination to the number of degrees the map says to compensate. And so every time you read the compass, you're compensating for the deviation. And if you have a target that's 10 miles away or 5 miles away, caving, maybe a half a mile in the woods, you will get to it. I found this to be very important to me because of I think the screen needs to go up. I found that very important to me because most of my use with the compass has been reading maps and bearings on property lines. At GSP, for instance, we often walk around over the decades to see where our line is, and the map says go 125 feet north, 30 degrees east. If I didn't adjust for the declination, then by the time I finished walking 135 degrees, I wouldn't be exactly at the spot where the next bearing would be. I would be off. Not much.
When there's question.
But I would be. Yes, Bo?
Oh, when there's so when you have like an old, like, okay, you get a walk north X feet and that measurements from 50 years ago, do you have to do an extra step there? Like that was north 50 years ago,
you don't
right?
have to do an extra step, but I see your question. If the property bearings are fixed, they were written down, like you said, 50 years ago, north 30 degrees east or something like that. You're going to go to the property now next month, next spring, and you want to take that same bearing. What you have to make sure of is your declination is adjusted for, and you will still get to the right spot. If your declination isn't adjusted, you won't be on the end of the property, right, at the end of the property distance. You'll be off. But you don't, as long as you've adjusted for declination, you won't make a mistake because the property lines are based on geographic locations, the grid system, the imaginary grid system that is on the Earth. The magnetic pole drifts around. So in order to make sure you're always on the same spot on the grid, you have to make sure your declination is adjusted.
That makes sense.
Does that make, okay. That's why I'm saying it's hard to convey some of this just through a virtual little meeting like this. Once you're out in the field and you hold a compass and you start sighting and you look at the cliff line over there in the distance and you look at a map, it kind of clicks. It suddenly clicks. The other thing to say crossed my mind just now is, GPSs and all the stuff we use that uses satellites and needs battery power and whatever. It's cool technology, but the compass still to me is the sexiest thing because it doesn't require any electrical power. It uses the Earth's force field. It's always there. It's always reliable. And it's the only kind of compass you can use with your caving. You can't use anything but a magnetic compass for that. It is susceptible to deviation if you put your metal watch too close to it, or you're going through a cave made of magnetite, you get a lot of iron ore in your cave, it's going to screw it up. But there's not a lot of that in Kentucky or in most limestone caves. Let me see here. What was I going to say? Something about that tracking targets. Yeah, so when you look at a map, you'll always see true north, which is the graphics, the magnetic north, and sometimes you'll see a thing called GN, which means grid north. That isn't so important for surface navigation. That's important for understanding how the map is done, what the projection of the map is. You remember that in school they had a Mercator map of the world on the wall, which the world is flat. It's a big square rectangular thing, and Greenland is the size of South America, and Florida is as tiny as it can be. That's because the longitude and latitude lines have been distorted. Latitudes, of course, were still horizontal parallel, but the longitudes are now all a bunch of vertical lines several inches apart from each other. So it distorts the view of the continent. It makes it different. So a grid north on a map is telling you that this is a flat map, but remember, it's the surface of the Earth. So that area of the map is actually has a curve to it. So that angle on the grid is what you would want to correct for if you're doing a lot of works with maps rather than out in the field. There's a way you can deal with compasses on maps if you know what your targets are. But if you are trying to figure a path to go, you use a compass to get a bearing, just like in mapping a cave. You really don't know what your target is in the cave. All you're doing in a cave is shooting until you hit a wall where you can't see around it anymore. Then you shoot another one, you shoot another bearing and another bearing, and you build up all this data of bearings, and then you connect the dots at home or on your computer. In my day, it was on a drafting board. And then you say, okay, so the trend of this cave, according to all my compass readings, is kind of northeast. Now let me get the topo map out, and I know where the entrance is because we went into sinkhole and I see it here on the map. So I'm going to put the entrance of our map on the sinkhole, oriented according to how the map is. If the passage has trended northeast, I'm going to make sure that I got the map aligned up with north, and my topo aligned up with more, and my cave map aligned up with the bearing. But remember, with a Sunto, there is no compensation for magnetic declination. All you're doing is getting a trend. So when you put that map over the cave map and you overlay it on the topo, it really isn't geographically accurate where it's ending. Is any of that coming through? It's actually off. If it were in Kentucky right now, Kentucky's also about 6 degrees west. So if you were to put that map on the topo in its trend from the starting point, you would then have to adjust the entire cave by 6 degrees east to make up for the declination. That means that the end where you stopped in the cave, assuming you didn't get to another entrance, but if you stopped in the cave and at your last data point on the map is whatever it is, quarter or half a mile away from the beginning, then you look at the map on top and you say, well, that looks like it's in the side of a cliff over here, according to topo. But if you adjust it by the declination, which you didn't compensate for while you were surveying, now the end of that stopping point, well, look at that. It falls right into a sinkhole up on top of the cliff. That makes more sense. So the information that you're gathering about where you're going, what you're steering to, what your destination is, what you're trying to find is all based on the geographics of the planet, the north, the longitude and latitude. And the declination is just something you have to know to compensate for the actual location on the surface. Once you do it more, or on the surface, hiking in the woods, it makes more sense. Made a lot of sense to me when I was first using a compass and I didn't compensate for the declination. And I would get to where I thought I would be, but like there was an out west trip and I said, we're supposed to be in the parking lot down there. We're up here. The parking lot was right. The information was right, but my compass kept telling me to go to magnetic north, not to geographic north. Now that I understand it, I can get to the damn parking lot. The other thing that's really cool about a compass, which is a practical thing in real life, is if you're going in some strange woods, and this is in areas where you can't see very far, you know, out, if you see long distances, you can just use your eyes to see where the hell you're supposed to go. But we went to a cave in Mexico in a, I call that more than a forest. That was a darn jungle. It was thick to walk through. And some locals told us about where to go on a trail, very small trail, more like a deer path. We went probably a 35-minute hike, found this cave in the middle of this jungle, had a great time, came out. But on my way in, I kept reading the compass to see what direction we were going. Because I knew if we come out in the pitch dark, we won't know where to go. We'll be lost. And it was so thick, you couldn't even look up at the stars to get a bearing. So when we came out, we had like 6, 7 people, and we scattered like roaches in the forest. Everybody said, this way, that way, that way. All I had to do was know that we trended northeasterly on the way in. Therefore, we must go southwesterly on the way out. So by using a compass in the middle of the night and believing it, I got out to the road in about the same amount of time as we got in. And other people finally came out because you're yelling to each other in the middle of the night. And there were people that came out on the road a mile down. But the compass is what kept me from being lost all night in that jungle. So that's a good way to use a compass. Take a breather. Any questions? Any thoughts people had? There's another term about compass that's called inclination. I probably should say that too to round everything out, but I'll take a break here.
Does anybody have any questions online?
I'd love to do this actually in the field for people who would like to get more familiar and comfortable with using them. Have you all mapped caves, I take it?
I know Bo and Kaylee who are on here. Terry, you were in the class. Anybody who's interested in cave mapping, we've got Greater Cincinnati Grotto leading trips into Climax Cave to do cave mapping. So this weekend we actually have a trip, I think starting at 9 a.m., meeting up at GSP to go work on some survey for that. Bo is heading up a Facebook group on that called GCG Project Cave Course, if anybody's interested in progressing cave mapping skills.
And just getting a new map of Climax Cave, which is much needed.
Compasses are also, they're very old technology, and they've evolved in their engineering and their sophistication, but they're still just a needle that floats on a balance point. In our latitudes, a compass's inclination adjustment is not very relevant. I've been talking about declination, which is the angle between where magnetic north lies and geographic north lies. But you all remember the drawings of a magnetic field from a bar magnet, the lines of force that come out of the North Pole, go around and go into the South Pole. You all have that image. And it's not two-dimensional. It's just all over, just like on the Earth, it's everywhere. Well, where the magnetic lines of force come out, they come out rather vertically, kind of perpendicular from the Earth, which is why the auroras all happen in these polar regions, because the magnetic lines are perpendicular, which is a line of sight from a ground dweller, somebody in Iceland. The particles, the neutrinos and other cosmic rays that come into the Earth, they follow these lines of force, and due to other physics stuff we don't have to talk about, but they emit light from the action that they follow the magnetic field, and that causes the aurora borealis. But as the magnetic fields bloom out of the planet and start making this big arc around to the other pole, these forces away from the pole are more parallel with the Earth rather than perpendicular. That's why we don't see pretty lights in the sky from the magnetic fields. And the closer you are to the Earth's surface, the more parallel it is to the Earth's surface at the lower latitudes. As the magnetic field enters the Earth, it dips, it goes into the Earth. That means that if you had a compass very close to magnetic north, it's not only going to point to the North Pole, or I mean to the magnetic North Pole, but it's also going to want to dip down because it wants to follow the magnetic field, which is also dipping down. And if the compass doesn't have enough of a bearing surface, enough room for the needle to move around, it can tilt so much inside a compass case that it rubs on the inside and would dampen the effect of the needle. It wouldn't give you a proper reading. That makes sense?
Yeah.
I hope. So inclination is important at very high latitudes where the magnetic field is dipping harder into the Earth. And down where we are, it hardly dips at all. So the needle has a lot of room. That's why needles are balanced not only to go round in 360 degrees, but you can tip a compass in any direction for a little few degrees, and the needle can still float around. So very sophisticated compasses on ships, especially the old galleon ships in the 200 years ago, they were building big gimbals, mounts, and really sophisticated. I would love to own one of those things. They were in gimbals so that when Shackleton was in Antarctica and he used his compass, he needed that gimbal for the compass to compensate for the field being a hard dip.
Real quick, based on that comment, do you have a particular brand or type of compass that you recommend?
Yeah, I have been very happy with the Santo. There's another brand that's equal to it.
How do you spell that? SANTO?
SUUNTO.
Okay, I would not have guessed that. Thank you.
Yeah, I think it's from Sweden. I think the compass is made in Sweden or Switzerland. I should know that, but you got me. I don't know right now.
Was it the Brunton is the other?
Brunton has been around for a long time. That's a very good compass. I don't believe the Brunton has a magnetic deck adjustment to it. But again, it depends how you're using a compass. If you're just out in the wilderness and you want to take a reading to some mountain, these Landsat compasses, this is called a Kamenga. These are issued to military people. The soldiers have these all the time. And they're out there carrying 60 pounds of ammunition and lives, you know, all their backpacks and all that. And they're told you need to go over to this mountain here and route out these insurgents or whatever. They're going to take a compass reading and say, okay, that mountain is at 45 degrees. They don't care about declination. They don't need to care about it. They just know their compass says that mountain is 45 degrees over there. So when they start hiking through the jungle and get into a valley or have to go around a cliff or avoid the alligator swamp or some crap, they know that, all right, I need to get myself back at 45 degrees because that's where that mountain was. And they'll get there. They'll get there. For that purpose, steering yourself to a distant target, just like in a cave, you don't care about deck. You just want a bearing so that you can move and make the map and get farther on. That's all you care about in the cave.
And that one, what did you call that compass? A Kamenga?
Yes, it's called a Kamenga, Cammenga, and the most common one that's issued is the Model 27.
Okay, thank you.
They have one that's got tritium in it that glows at night. It's super cool, but it's like $80 more. And I don't do a lot of compassing at nighttime anyway. So, but it's cool for the soldiers. They're all into that. The other one starts with an S2, Santo, and
Okay. This. Hold on. I was thinking it was Brunton's, but it's not. Hold on. Let's
top
see.
3 compass brands or something like that.
This.
Top 5 compasses of 2023.
I've used mine mostly to confirm property boundary lines in the woods down in Kentucky. And over the years, it's been darn accurate. Each boundary change is often marked by some benchmark on the description, like go to the forked beech tree or go to the metal rod placed in the creek rock. And you're in the middle of the woods and everything looks the same in a certain way. But after hiking 25, 30 minutes over everything and walking through briars and trying to stay on your path, and then you realize, okay,
It's not that. Is
here.
it? Sport near?
No, it's not.
That's not that.
It's and then you see the rebar in the middle of the woods. There you see it. You think, okay, I guess I'm doing it right because I just found something that I would look forever for if I didn't have one.
Werner, can you show us what you're looking at when you're looking at a compass?
Yeah.
Because there's the mirror in it, and I've never quite understood what you're looking.
Yeah, well, let's see if we can do this with the
Sylvia?
Sylvia, yeah.
Silva.
Silva.
It's Silva. That's, you asked me what brand compass. I use a Santo. I like Santos. I use them in caving. But Silva, Silva, they also make a compass that's virtually the same. It's identical.
Yeah.
I like the Santo because they use a glycerin inside their compass needle that calms it down real quick. When you want to get a bearing, you don't want a needle to bounce around for 30 seconds. But on these base plate compasses, what you do, it's so hard to show here, but at the bottom of the compass plate, there's a painted arrow and it moves with the dial. It moves. That painted arrow into the dial represents where true north is. And the magnetic needle that floats on top of it, that magnetic needle that floats on top of it, it's really hard to see here. You have to turn your body until the magnetic needle, the north end of it, is directly over the painted arrow.
Okay.
Then you've got magnetic north and geographic north lined up. Then once that happens, you hold the compass to your eyes, you orient the mirror so that when you're looking at the mirror, the dial is being reflected to you. You can see what the dial says. And you sight the target in the distance, like a cave entrance or a shelter or a mountain or something. You sight through a hairline right above the dial and through the case. There's a hole there. And then you look in the mirror and make sure that your needle and your painted needle, your magnetic needle, are over the top of each other. They're directly in the same point, same spot. That's when you look at the dial and you read the degrees. So if I'm looking at an object in the distance and I sight it, then I turn the magnetic north, or I turn the painted needle in underneath the magnetic needle so they're lined up. I know that I've got this compass lined up with the two arrows. I look in a mirror, which shows me the dial, and then I read what the number is at the target line. And what I'm doing right here in this example, it just so happens that Stephanie's fireplace is right north of me, directly north. Is that north, Stephanie?
That is north, and actually that's North Bend Road, so that it makes 100% sense right
So,
now.
and if I sight over to her coffee pot, I do the same thing. I turn to magnetic, or I turn to painted arrow underneath the magnetic floating arrow. And then I sight to her coffee pot, and then I can look in the mirror, or right now, I'll just look down. And her coffee pot is 98 degrees off of north. So her coffee pot's east of me. So it's obvious here in the city where everything is laid out on a grid and we have maps, we know where north, south. But in the woods, you look all around 360 degrees, everything looks alike. So that's when a compass really helps. I mean, let's face it, we all in our everyday lives in the city, driving around, walking around, we don't look at a damn compass. We know where we are. We know where we're going. We know the maps. We know our neighborhood. We don't even care.
Mhm.
And a lensatic compass works similar, but instead of using a mirror, it uses a little magnifying glass here. And you have to hold this sucker right up to your face so you can get your eyes on that lens. And it's 45-degree angle on the lens, and you look down and that's 6 degrees. That's how you read it.
Okay.
No mirror. The base plates have mirrors. This doesn't have deck adjustments, but this does. Oh my. It's a lot more fun when you're out in the woods. Take my word for it. It really is. And compasses are great. Some people are into geocaching.
Yeah.
I've never gotten into that. I think I would like to. If I'd been younger, I probably would have gotten into it. But it's really cool because they'll give you readings, they'll
Yeah.
give you directions. And so you have to start at some wherever point you start geocaching, from some parking lot, I guess. And they say you have to go so many feet north or east or whatever. You got to know how to use a compass to find your way to those spots. And it's a lot of fun. It gets you a lot of experience. Well, I imagine I've filled enough brain up right now. Questions, any questions? Otherwise, we'll plan this again outside in the field sometime in a warm.
Yeah,
warm
that sounds like a great plan. Maybe down at GSP, we'll go play in a field, or maybe up here in Cincinnati, we'll go play in a park or something like that as a grotto.
I do have another section of the property boundary that I want to confirm because of some timbering that was done last fall.
Oh, well, now we've
We
got
could
a
all walk up there.
bunch of
and-
people who are
yeah.
interested, so.
And we need, it isn't just directions of the property, you need distances. They might give you a distance of 1,500 feet. So somebody's yelling to walk 1,000 feet and then telling you, go to the left of this tree, go to the right, go over this rock, whatever, so that you stay on your bearing.
Question for you, Warner. Why, yeah, like normally when I think of like property boundaries surveys, I'm just thinking of maybe some GPS coordinates and, you know, plotting between them. Why would I need to use a compass and bearings for mapping out property boundaries?
If you have a smartphone and you have the two bearings, you can walk in the woods. Your phone has a compass on it. So it's going to guide you. You're just going to follow what the phone tells. It's the same problem, or not the same problem, but it's the same thing where if you're driving and you want to get to Stephanie's house, you punch in a target locker road, and the satellites, the GPS, they immediately say, okay, you're here, she's there, take this route. You're going to do that. You won't need a compass because you have that technology.
And then, well, I guess, should I say, I guess I'm trying to get to is before I surveyed with you in the GPS, I mean, the GSP boundary, I didn't realize that boundaries were what I've seen, where it's look for this oak tree
Yes,
and walk X number of feet.
right.
So that was all new to me.
Yeah, those are, well, in Kentucky, that's, people have property from 100 years ago and they measured by rods and other chain, like 15 chains. And I had to look back, what the hell's a chain? Well, a chain is 16 feet nowadays. So 15 times 16 feet, that's the distance of the boundary. And like one section of the property follows what they call snail drain, which is a draw, and it's a creek that goes down. And when I first looked at the property map, I didn't know that was a drain. I just looked at a map and it said go 20 feet north 13 degrees, go 18 feet north 15 degrees, go 5 feet northwest 7 degrees. And that went on like for 50 readings, just on and on. And but you never met more than 10 feet or 15 feet or 20 feet. I said, what the hell? Why would they not just make one long straight shot and say it's 300 feet down the hill? Because they followed the creek, and the creek has jigjags and follows the topography. And at that time, they sighted to every little bend in the creek to make sure that a landowner says, your property is on that side of the creek and mine is on this side of the creek. If they just did a straight line and the creek made a bit elbow, somebody going to say, hey, you had your goat eat the grass on my side of the creek. Get your. So they were very specific about some of their property boundaries. But then when I went to the field, when I actually went out in the woods and looked at these bearings and then looked at the ground, oh, it's the creek. I don't have to read every one of these. I'm just going to go to the bottom of the creek. So get yourself an inflatable earth and learn this stuff.
All right. Well, it sounds like we're gonna schedule a program sometime in the spring where we work with Werner to map out the property boundaries at GSP. So for everybody here who's interested in that, keep an eye out. We'll put an event out somewhere on GCG's Facebook page probably, and just hopefully we can meet up and do some of this compass and navigation in person. Get some practice. All right. Does anybody have any other questions
or comments? Otherwise, thank you.
All right. Thanks, y'all. On behalf of Greater Cincinnati
David.
Grotto.
Wait, what?
Was that a
I was just
question?
saying thing.
Oh, okay.
No, I was just thinking. I have a question real quick.
Yeah, go for it.
How does, or how has compass navigation and methodology changed with the improvement of lasers and laser sighting and laser range finding? Use them in conjunction with each other, or is there not a lot of overlap there?
Oh, it's definitely in conjunction. What's happened over the recent generation is because of the computerization of things, that the accuracy has greatly increased. The magnetic North Pole has to be programmed into even the most sophisticated instrumentation, including space probes, everything military on land, sea, or air. In fact, the magnetic North Pole has to be put into these programs and tracked virtually hour by hour to maintain the accuracy of allowing, like the James Webb Telescope, to get out exactly where it is, or the probe that just hit an asteroid, Bennu, and then picked up the rocks and came back. All of that is based on understanding our magnetic field and how it changes in the Earth, and that information is programmed. The compass itself is very elemental, very basic. It's a freaking piece of metal floating in a liquid, or sometimes not even that much. So the methodology part, it's all about understanding magnetic North Pole and how it moves and drifts around. the geographic north was established when we came up with the grid system centuries ago. That hasn't changed.
I have two questions. Do you have to, depending on your elevation, and like, I'm thinking of great changes to elevation.
Yeah.
Do you take that into account with regard to,
No, the airplanes.
Yeah.
They have, I don't understand, and I don't purport to understand the technology that goes into civilian or military aircraft, but suffice it to say, it's way more than what a Santo or a Kamenga is. But the higher you are on the planet, the more you would have to compensate for things like inclination, the magnetic fields, how it dips. And the field is not like what you see in your drawings. The field is a very dynamic, fluctuating thing. It's what it's created by the rotation of the earth, which has different speeds, the core in the middle. It affects everything on land. It affects animals. It affects us. It affects light. Magnetic field is very pervasive, and high technology equipment nowadays, they probably using advanced physics laws know exactly how to understand what's going on at a given location in the planet, whether you're on the surface or 1,000 feet in the air. You know that if a rocket ship launches, they know exactly where they are in every possible way every second. And they can predict where they're going to be in 10 years. So was that one question or two?
well, I think you just answered my second question, which was, can, uh, uh, can the magnetic north be extrapolated / has it been accurately calculated?
No, it can only be, they watch for the trend. That's a good question, because I had that question too back when it finally had my head wrapped around. The magnetic field is created by all the dynamics going on inside the earth, the pole, the North Pole. And you can go to websites, you can go to old documentation, like you can tides, remember way back, you could see what tides have done the last 200 years. You can figure what they might do in the next 50 or more. The same is true for the magnetic North Pole. They've tracked it for generations now, and there's even a website that shows animation how it drifted around the top of the world for the last 100 years. And it doesn't look like it's anything particular. It's not like, oh, it's the infinity loop or something. It's just very random. It goes wherever the heck and they predict where it might be, but until it's there, they don't know. So every few years, if you buy a topo map, my topo map of Livingston, Kentucky, which is where GSP is shown, had a magnetic declination in 1969 of 0. No adjustment needed on the compass. It is now at 2022, it was -6 degrees west.
Wow.
Now it's a year later, it might be 6 degrees, 4 minutes west.
Uh-huh.
It changes constantly.
That's interesting.
And then with regard to like all digital compasses, or let's think about like the digital compasses that we may use in cave, non-internet connected.
Right.
Is the declination, how should I say, is that something that you manually input, or is that something that is?
I don't know about the digital compasses.
Yeah, Stephanie's gonna go. Like I know when you why am I trying to get the name of it? When you calibrate it.
Calibrate,
If
yes.
that is part of the calibration process.
So they have these with the survey devices that we use, like the brick and some of those other items. This is a Shetland attack pony. These are now our Grottos loaners. So
This looks like something I would
it's
get
3D
a shot
printed.
from Dr. McCoy and Star Trek.
So, yeah. So it shoots a laser and it should take the measurement of, and I have not calibrated these, so it may just be angry with me.
Well, my car, for instance, has a compass, as most of them do. And once in a while, they'll tell you how to calibrate your car compass by going in a parking lot and driving in circles 2 or 3 times, which I've done.
Yeah.
And you can watch your cardinal points appear. You hit the calibration program in your car. Got to read the owner's manual. I'll never remember that. And then you drive slowly in circles. And as you drive, you see north, northwest, west, southwest, and it just keeps, you do that 3 or 4 times, and then you're calibrated.
Mhm.
Now, whether that car program knows that we are -6 degrees off from true north, I don't know.
Mhm.
Maybe someone listening does. I don't know.
Yeah.
But for purposes of driving on a gridded system in a city that I can only go on streets,
Yeah.
I can't compensate for declination because that will go through somebody's rose bushes. I just don't worry about it.
Yeah, fair enough. Cool.
Thank you.
All right, folks. Thanks for joining. Message us online if there's any questions or concerns. We'll get um, a date scheduled for helping at the GSP to look at the boundaries. Sounds like we've got a cool little project application that we can do. And join us December 5th. We have our next Tech Topic program. It will be the Knots Clinic. So that's a very popular program. And we'll practice all of the NCRC knots. That'll be, again, December 5th, 7 to 9 p.m. We will have an online session, but if you're able to attend in person, that sometimes is a little bit easier for folks, and we'll have rope for folks to play with. Otherwise, thank you guys for joining, and follow us, I guess, on Greater Cincinnati Grotto's Facebook page.
Hey, Steph.
Uh-huh.
There are some
Thank you.
comments
Oh.
that are asking if it's possible to get the links elsewhere that from people that aren't on Facebook.
Okay. If you're in GCG, we can probably send it out through our Greater Cincinnati Grotto email chain. If you're not a Greater Cincinnati Grotto member, how to get on that email distribution would be to join the Grotto. And you can find us on the website, the Greater Cincinnati Grotto's website. Otherwise, that's our main source of contact is through that email chain with the Grotto or through Facebook. Okay. And it looks like Dennis put the link gcgcavers.com in the chat. So if anybody's interested in joining the Grotto, that would be the link for that. Cool. If there's no other questions or concerns, thanks for joining. And I think this recorded, so we might be able to upload this program to YouTube. Thank you guys. All right. Bye.